would put us to 10:40. All right, I guess not. I'll talk to him later. Here we go. All right, welcome to Entanglement 2. If you missed Entanglement 1, sorry, go back and check it out. It's still there. Unlike most lectures, when you come in late and you miss the first half of the lecture, usually it's gone. You can't ask the student next to you to play it back for you, but here you can. We have a network error, excuse me. Let's play this. Okay. So this is Entanglement 2, the second half of a lecture being taught at Michigan Tech. The course title is Physics X. The official title is Extraordinary Concepts in Physics, and I'll explain the stuff that I and other people think are cool using just Wikipedia links. 4 credit for students here, but anyone who's interested can tune in. So this time I'll start off with some things that bothered me in my struggle to understand entanglement and double slit experiments in quantum. So let's start off. I like to go with experiments because they're somewhat ambiguous. The experiment says this or that. You can build your understanding based on experiments. That's rather basic. So these 2 experiments, I'm pretty sure I know the answer to, but I don't know if they've been done in detail. So you have one positronium photon. If you don't know what positronium is, you can back up to last lecture. Goes through a classic double slit experiment. Well, its entangled twin goes toward a very near image screen. So here you have positronium here, boom. And one photon goes in this direction, and one photon goes in this direction. And so here you have, in this direction, you just have an image screen. And in this direction, you have a double slit experiment. A slit screen. And here you have image screen. But this distance here is small. Therefore, the entangled photon, which this is the other photon, this is the other photon, entangled photon entering the double slit experiment still has the opposite momentum, but now this momentum could allow it to enter either slit. This identical situation is repeated numerous times. What will the image screen behind the double slit experiment show? What will this screen show? So we know, so we're trying to outwit, this is an attempt to outwit the double slit experiment. So here you got a photon coming here. Okay, it's classic double slit experiment. But now I'm going to do the double slit experiment with an entangled twin, and I'm going to figure out which slit that double twin is going to go through, because I'm going to figure out where the entangled twin goes, and that's going to tell me where the first photon goes. So I'm going to beat the double slit experiment without touching the photon. So in this case, we're warming up, and we're going to do a nearby image screen and say, okay, let's see if we don't know it first. Could we have known it? So the answer is, so here's the possibilities. An interference pattern could appear on the image screen, which I usually draw like this. No interference pattern, which I usually draw like this. Let's see. There is not enough information to tell, or positronium explosions will destroy the entire experiment, so it's really senseless to continue. You need to call the medics at this point. All right, so the answer is interference pattern, to the best of my understanding. The entangled twin does not carry which path information. Therefore, there is nothing that will destroy the interference pattern. So I believe that you will get an interference pattern here. All right? So let's go around again. This time, it's the same text as last time. One positronium photon goes toward a classic double slit experiment, just like the previous slides. The entangled twin goes to a very distant image screen now. So we're going to take this screen, and we're going to cross out small, and we're going to put big. So this is a very big distance. This is well across the hall, down the hall, next building, across campus, on the moon. So once this image screen is far enough away, shouldn't you be able to tell where this photon is going? And then you say, oh, wait, this photon has the opposite momentum. Therefore, I'm going to know which slit it's gone through. So I'm going to figure out whenever it hits this screen here, it hit it there, that means that on this side it went through that slit. So even though there's an interference pattern there, I'll have beaten it. I'll say, yes, maybe there was an interference pattern, but I know which slit each photon went through. Does this work? What will the double slit experiment show, for one thing? Will it show an interference pattern? Because how does this side know what this side is doing? Does it show no interference pattern? Because now information about which slit the photon went through is available. Is there not enough information to tell? Or have you really stopped caring at this point? You might try that other window where there's a nice Dilbert comic. Okay, here we go. To my best understanding, there will be an interference pattern, and the reason why is a wiggle reason, not an amazing reason. It turns out that the location of the positronium explosion is not going to be known all that well. So even if you were able to locate the entangled twins location on the distant screen infinitely well, you would still not know which slit its entangled twin went through, and there will still not be which-way information. And the most similar thing is if you go back to the early lectures of this course, you can find a slide labeled Einstein's slit, where Einstein himself tried to beat the double slit experiment by incorporating the momentum of the slit screen at the same time. And Bohr showed no, that even if you incorporate the momentum of the slit screen, you still can't beat that, and you will still get an interference pattern. So in this case, tracking the entangled twin, I believe, will not allow you to know which way information. You will not be able to beat the interference pattern. All right. This is a review of another slide. Counterfactual definiteness is the ability to know a result of a non-local experiment, definitely given the result of a local experiment, even if the local experiment did not measure anything. So an example is, again, you have a positronium, you have a photon emitted here, and you don't know which direction it went. And there's an inner shell and an outer shell, and you are able to tell if it hits the inner shell. So the photon goes off, and you know it doesn't hit the inner shell because there would be a flash. So you know without even touching the photon that it's going to hit the outer shell. And that's an example of counterfactual definiteness. And there is examples of that in quantum mechanics, but they weren't the last few slides. So it is possible to know things about photons without measuring them, which was a big change for quantum mechanics, because when Heisenberg quantified his uncertainty principle, and most people believe this as the uncertainty principle, and many physics textbooks repeat this. The uncertainty principle is due to measurement error, and that when you touch something, you destroy it, or you create something strange about it. But you can learn something about things without touching them at all. And the basis of that, the basis of quantum mechanical uncertainty is that, and not observer effect. And one example of that is counterfactual definiteness, which works. All right, so let's go into hidden variables. Bell's theorem. So Bell thought a lot about this, as I said last lecture. He was worried about hidden variables, that things like momentum could be encoded beforehand. And so everything is encoded at the initial explosion when there's positronium being exploded and there's two things going out and they just have opposite stuff. So if everything is encoded here, you don't have to have even quantum mechanical statistics, Bell found out. That was his real contribution. Knowing that hidden variables, bells and whistles on electrons and photons, things created right at the explosion, create their own statistics that cannot be denied. But that quantum mechanical statistics, when something is measured, it's a quantum mechanical phenomena and might have quantum mechanical effects far away or something. Quantum uncertainty is not based on the lack of past knowledge, Bell was wondering. Bell kind of thought, well, I don't know exactly what Bell thought, but he coined a theorem and an inequality that enabled people to go off and measure that eventually. Again, usually using spins, because spins are a good way of measuring things. So now let's talk about Bell's theorem of entanglement. So Bob and Alice, who we met last lecture, can choose individually to measure each spin vertically or horizontally, like they did last lecture. If they choose the same, like I reviewed last lecture, they get opposite spins with a 100% chance. If one chooses vertical and the other horizontal, they agree only 50% of the time. So that's part of this. The other part, as I repeated last time, is that if Bob doesn't even know if Alice is awake over there. Bob is measuring 50% up and down, having no clue what Alice is doing. And the quantum mechanics is only found the seeming faster than light transport between the two particles, that one was measured spin up, so the other one must instantly be spin down. Bob doesn't know what's going on. Alice doesn't know what's going on. They're just getting ups and downs. Only later, when you compare their data, do you find, wow, this one was up and that one was down, always opposite. Now, what Bell realizes is that if they're exactly opposite, then you can't tell. if you measure right on the axis, x-axis, and if they both measure on the axis. If they both measure 90%, it's also hard to tell. But in the middle, say at 22 degrees. So you're measuring now, here's the z spin axis, say. But now you measure things around a different axis. Let's say this is 22 degrees, 22 and a half. You get different statistics, Bell realized. That hidden variables was always going to give you some statistics, some projection operator of what the spin is. You project the spin, you get an answer. But quantum mechanics works differently. Quantum mechanics gives you a different percentage. So you can go and you can measure which statistics do you get. Do you get the hidden variable statistics involved with projection, or do you get the quantum statistics involved with what seems to be faster than light in knowledge between distant particles? Oddly enough, it was shown, even recently, these experiments are ongoing, that quantum mechanics is right. And that even people who believed hidden variables and local realism were wrong. So quantum mechanics actually shows that local realism is essentially wrong. And local realism assumed that either, well, both possibly, objects have a definite state that determines all measure properties, hidden variables, and or the effects of local actions cannot be transmitted faster than the speed of light. But it does seem that when you measure spin up here, that the other one immediately knows to be spin down. They seem to know instantly. It's as if they're the same particle. It's as if there's like some other strange dimension where they're not separated by any distance at all. And we measure one and the other one comes about right away. This doesn't mean, though, that you can communicate faster than the speed of light. Because all you can do is measure. You can't tell your electron or photon to be spin up. You're going to get 50% either time. And Alice, if you're Bob and Alice is going to get her 50% either time, you cannot communicate that way. But it seems that the particles instantly know from one to the other. And people are now trying to determine if there is a speed limit on that, which is much higher than c. But I guess the common wisdom is that it's essentially instantaneous. The way I think about it is that they are entangled. They are essentially one particle. It's just they're not locally. They're not local, at least in the dimensions that we're familiar with. And with that I have to bring the unsatisfying, perhaps, end of this brief discussion of entanglement in Bell's theorem. That's essentially what it says. Bell's theorem seems to say that quantum mechanical calculations are right and that local realism is wrong, but still does not allow faster than light communication. So see you next time with even stranger stuff.